In this video, we're discussing molar volume, and we are talking about the volume of a gas, so we're still talking about gas substances. So remember when we talked about molar mass, that's the mass grams of 1 mole of a substance. So similar to that, when we say molar volume, we're talking about the volume of a gas, liters of a gas in 1 mole of a gas substance. These are your learning targets. So what I want you to do first is, using the ideal gas law, I want you to solve for the volume of 1 mole of a gas at STP. And STP stands for standard temperature and standard pressure. So if you remember from our previous videos and our previous notes, standard temperature is 273 Kelvin and standard pressure is 1.00 atmospheres. So I want you to go ahead and use our ideal gas law, PIV-NERT, and plug in the values, right? Define our values and go ahead and solve for this. What will you get for the volume at STP? So go ahead and pause the video and try to work this problem yourself. Go ahead and unpause when you're ready. When you define your variables, you have 1 mole for N, you have 273 Kelvin for temperature, you have 1 atmosphere for pressure, and remember the pressure unit will tell us the universal gas constant R, so in this case pressure is atmosphere, so we'll be using 0.0821, and volume is what we're solving for. So let's go ahead and plug it in and solve, and you will get a volume of 22.4 liters. So this is telling us that the volume of any gas at standard temperature and standard pressure, the volume of any gas is 22.4 liters in 1 mole of that gas substance. So now that we saw for the volume of a gas at STP, let's now calculate the density of a gas at STP, standard temperature and pressure. So example 1 states that an ideal gas has a density of 3 grams per liter at STP. What is the molar mass of this gas? Well, when you see the words STP, I want you to think about the molar volume that we just solved for, which is 22.4 liters per mole. Now, previously, we derived our ideal gas law so that we are able to solve for molar mass, right? So you could actually plug in all your values for this and solve for molar mass, but what we just did was we went ahead and figured out this right here will give us 22.4 liters per mole. So basically, we can actually take this formula and rewrite it as this. Density equals the molar mass over the molar volume. What does this look like? It's your typical density formula, right? Density equals mass over volume. And whether you use this formula here or this formula here, you will get the same exact answer. Why? Because the conditions are at STP, standard temperature and pressure. So we're going to use the density given, 3 grams per liter. The molar volume we just determined is 22.4 liters per mole, and we can solve for the molar mass, right? So the molar mass of this gas is 67.2 grams per mole. Now go ahead and try example 2 on your own. What is the density of carbon dioxide at STP? You should have gotten an answer of 1.96 grams per liter, right? So in order to get the molar mass, you got to think about the carbon dioxide, CO2, add up the masses there, and that's your total molar mass. That would go on top, so that would be the numerator, and the denominator would simply be 22.4 liters per mole. Okay, and you get your density answer that way. Now, let's go to this picture, 1 mole. Now, you might remember this picture because we used it earlier in the year, right? Previously we said that 1 mole is equal to Avogadro's number, which is 6.02 times 10 to the 23 particles. Remember, there are more words associated with that. So you could say particles, molecules, formula units, ions, and atoms. So whenever you see those words, we are thinking about Avogadro's number, 6.02 times 10 to the 23 particles in 1 mole of a substance. Then we talked about 1 mole of a substance is equal to the grams of a substance on the periodic table, and this is known as molar mass, right? Now today, you just learned that 1 mole is also equal to the volume of a gas, which is 22.4 liters, and this is called molar volume, okay? And again, the conditions for this is STP, standard temperature and standard pressure. So whenever you see those letters STP, it really just means that you're going to be using 22.4 liters per mole somewhere in the problem. Okay? So let's take a look at our first example. What is the volume of 1.3 moles of hydrogen? This is a simple mole conversion problem. And how did I know that it's a simple mole conversion problem as opposed to a stoichiometry problem? Well, first of all, it's not even talking about a reaction, right? It is just simply converting 1.3 moles of hydrogen into the volume, okay? So we set it up using the fence. 1.3 moles is what we're going to start with. We're going to copy down our unit, so moles gets brought down. And what do you think we're going to put on top? Well, the problem is asking for volume, right? So volume we know is liters, so we're going to go ahead and put liters on top. And here is the molar volume. Liters over mole, that is the molar volume. So what is the molar volume that we just discussed? 1 mole is equal to 22.4 liters. So again, 1 mole, so where you see mole, you're going to write 1. Where you see liters, you're going to write 22.4, and your setup should look like that. Okay? Your like units cancel out, so in this case, we're just multiplying, and we get a total of 29 liters of hydrogen. Go ahead and try number 4 on your own. You can pause here because the next thing I'm going to do is show you the answer. And there are 1.50 moles of fluorine gas in this 33.6 liter sample. Let's take a look at our next example. Determine the volume of 22 grams of carbon dioxide gas. So we are going to start with 22 grams of carbon dioxide, and you see already that I have more fences here, okay? Because I can't just go straight from grams to liters, right? What do I always have to go through? I have to always go through moles. So grams will get copied down. On top will be moles. And again, I'm going to copy moles. And on top will be liters. So think about each fence, right? So this middle fence here, that you see is moles over grams. What do you know is moles over grams? That's the molar mass. So find the molar mass of carbon dioxide using your periodic table, and you should have calculated that the molar mass is 44.01 grams of carbon dioxide is equal to 1 mole. So you look at our third fence. Here we have liters per mole. So you see liters, and it's over a mole. Well, that should automatically trigger molar volume. And again, the value doesn't change. It's 1 mole is equal to 22.4 liters. Our like units cancel out. You multiply and divide, and we get 11 liters of carbon dioxide. And this is considering significant digits. Go and try number 6 on your own. How many molecules are in 33.6 liters of methane? Molecules, remember, is another word for just particles. So somewhere in your setup, you will have to use Avogadro's number. All right? So we can pause the video here. When you're ready, unpause. And the answer to this problem is 9.03 times 10 to 23 molecules of methane. Now let's take a look when we're given a balanced reaction. Okay, so we're going to do a little bit of stoichiometry with molar volume. So here's that same picture that we looked at with stoichiometry. Now what is different about this picture that we haven't seen before? We see liters of substance A got added in here and liters of substance B, right? Volume of A, volume of B. Other than that, the method is the same. Everything else is the same. You're going to figure out what is given to you in the problem, right? And that's where you're going to start. Where are you trying to go? What is the desired unit? And that's where you'll stop, okay? So let's take a look at our first problem. And if 6 liters of hydrogen gas are used, how many liters of nitrogen gas will be needed for the reaction at STP? Again, there are those letters, STP, standard temperature pressure. And again, it doesn't really mean anything except for the fact that you'll be using molar volume, 22.4 liters per mole, somewhere in this setup, okay? So let's do the same steps as before. We want to go ahead and write down what we're given and what we're trying to find. And we're going to cross out anything that they don't talk about, right? So we are given 6 liters of hydrogen. It wants to know liters of nitrogen. We can ignore ammonia right now because we're not interested in it. And let's bring up the picture, okay? So where are we going to start in this picture? Well, we're going to start right here, right? And we're going to ignore everything else that's on top, okay? Because it has nothing to do with this problem. And where are we going to stop? Well, it's asking for liters, right? So we're going to stop all the way over here. So remember, this picture tells us your starting point, your middle points, and your end point, okay? So let's start with 6 liters of hydrogen. Draw the arrow, and that's going to point to moles of hydrogen, same substance. Next arrow, moles of where we're trying to go, so moles of nitrogen. And lastly, liters of nitrogen. And we're going to go ahead and replace those arrows with the fence. And let's bring down our units. Okay, so here we have liters of hydrogen, so we're going to bring that down here. Moles of hydrogen, bring that down. Moles of nitrogen, bring that down. And now we can go ahead and put in our numbers, right? So here in our second fence, we have molar volume. Here we have moles over moles. Moles of one substance over moles of another substance. What do we call that? That's called the molar ratio, right? And where do we get molar ratio from? That's from our balanced reaction, right? So it looks like I'm putting in numbers here. So let's go over this first. So 1 mole is equal to 22.4 liters. And then our next fence, we have our mole ratio. So again, we're going to look at our coefficients. So we have here no number, but that means 1. And here we have 3, so it's 1 mole of nitrogen to 3 moles of hydrogen. And lastly, again, we have molar volume. So we're going to go ahead and plug in our numbers. 1 mole is equal to 22.4 liters, right? Our like units will cancel out. We're going to multiply and divide to get an answer of 2 liters of nitrogen gas. Okay? So you see that the steps are the same, right? It's just the word STP is now thrown in here, and we're using molar volume for these problems, all right? So let's take a look at example 8. You want to produce 14.25 moles of ammonia. How many liters of hydrogen is needed at STP? So again, you're going to write down what you're given and what you're trying to find. Okay, and then we're going to bring up this picture. And where do we want to start in this picture? Are we going to start from here? Are they giving us particles or grams or liters first? No, they're not, right? So we're going to go ahead and just cover that part up. And this is where we're starting. We're going to start at moles of A, go into moles of B, and we're going to go all the way to liters of hydrogen, right? So we're going to go all the way to over here. So go ahead and pause the video and set it up. Try to set it up yourself, okay? And when you're ready, unpause, because I'm going to show you my setup. So we start with our given, 14.25 moles of ammonia. We're going to go into our desired substance, moles of hydrogen, and out to liters of hydrogen. Replace it with the fence, copy down your previous unit, mole over mole, that's our mole ratio, 3 to 2, and again, liters over moles, that's our molar volume. 1 mole is equal to 22.4 liters. Cross out your like units, multiply and divide, and you get an answer of 478.8 liters of hydrogen. Go ahead and try the next one on your own. How many formula units of magnesium oxide are needed to make 25 liters of oxygen at STP? When you're ready, go ahead and unpause the video. So here we are starting at our first point here with liters of A, going into moles of A, moles of B, and formula units, the same thing as particles here, so we're going to end up here, okay? So let's go ahead and set it up. You should have something like this. Replace the arrows with the fence. Copy down your units. Okay, and then we're going to fill it in with numbers. Moles over liters, that's our molar volume. 1 over 22.4. Moles over moles, that's our molar ratio, which is 2 to 1. And then formula units over moles, remember that's where we use Avogadro's number. So 1 mole is equal to 6.02 times 10 to 23. Like units cancel out, and you get an answer of 1.34 times 10 to the 24 formula units of magnesium oxide. So go into the next example on your own again. Starting with 5.5 liters of chlorine gas, how many grams of magnesium oxide are needed? So using this picture, we're going to start with liters, and this time we're going to end with grams. This is what your setup should look like. That's the top part of your fence. Again, copy down your units. Moles over liters, that's your molar volume. Moles over moles, that's your molar ratio. Grams over mole, what is that? That's your molar mass, right? So the molar mass of magnesium oxide is 40.31 grams. Like units cancel out, multiply, divide, and get an answer of 9.9 grams of magnesium oxide. Our last example is a limiting reactant problem, just to review it, okay? So we're given 10 moles of hydrogen and 13 moles of oxygen. How many liters of water will be produced, and which reactant is your limiting reactant? So remember, this is the one where you got to set it up twice, okay? So let's start with 10 moles of hydrogen. And we are trying to find the volume of water, okay? Same setup as our previous problems, right? Get our molar ratio, molar volume, solve for that. You get an answer of 224 liters of water. We're going to do this again with our second reactant, 13 moles of oxygen. So we're going to set it up like this. Molar ratio, 2 over 1, molar volume, 22.4 liters per mole, multiply, divide, and get an answer of 582 liters of water. So remember, how will you know the answer to this problem? How much water is actually produced? Right, it's the smaller answer, right? So the smaller answer is 224 liters of water. That's how much is being produced. And our limiting reactant is hydrogen. So remember that the smaller answer tells us our limiting reactant. So hydrogen is our limiting reactant, where oxygen is our excess reactant. And that's it for gases.